worked on as many problems as I plan to work on for this particular cycle on chapter 3 of Mendelson and also chapter 4. Even though chapter 4 is a shorter chapter, I wound up doing a lot of problems in it because it's got to do with rationals. Some of the sections that had number theory problems, I skipped. Mendelson problems. About time, right? Because it can't be all that I just read, and then that's a lot of shadow boxing. And for this baby Rudin thingy, I have been doing way too much shadow boxing for my own taste. And shadow boxing, I mean just doing reading, which is very passive. And so, I have had a lot of fun working through some of the ring and integral domain problems. And then, of course, in chapter 4, we get down to business with fields with the irrationals. With the irrationals. Yeah, here we go. Rationals and ordered fields. So now is where I'm getting to flex a little on the field axioms within the context, of course, of rationals. And there's also some business about subfields. And just this moment, I just finished working on some of those problems. There is a harder problem that I also tried, which is the Cauchy-Schwarz inequality. This problem 6 here. It's got a D for difficult. And it is. Now, I know that there's a proof of the Cauchy-Schwarz inequality in Rudin, and I know I even looked it up in Wikipedia, but I want to forget that I did that in the sense that one of the skills that I want to work on, which I really have not done a great job, I've not done a good job at all, is working on harder problems and getting to the point where I have the oomph for the harder problems instead of basically chickening out and saying, well, I did some of the simpler problems and I was okay. And so there's a question of like, what are you better off doing? Are you better off doing 100 simple problems, 20 medium problems, maybe 10 harder problems, or just one very hard problem? I don't know. I want to do all the different options, but I also, I just want to develop that skill. So just quickly to remind myself of, why I embarked on this. I'm probably the only guy out there who's crazy enough to have read a whole book just to, Mendelson being that book, to have a better feel for the axioms. So just let me remind myself and all of us for where in chapter 1 this all happened. So in chapter 1, there was the business of order sets in Rudin, trichotomy, right? And then there was also the business of the field axioms for the real numbers. Well, actually, these are really the general field axioms that happen to apply to F. And F can be a real number system or complex. Let's be clear. This F is a very important letter in here. And so then Rudin later on instantiates it to, of course, there's the ordering part of the field, and then also instantiates it to the complex field. Just reminding that that's why I wanted to read Mendelson, but I got a little more than I bargained for, and I'm very happy about that. So now, where I left off when I was last, let me see if I can zoom out correctly. Yeah, I think that's the best that I'm going to get. Sure. Okay. So I left off around here last time, and I was working in chapter 3 problems, section 3.3. Continued on, a little sub ring business going on here. And then this is where I ended up looking at ChatGPT for zero divisors. I made a ChatGPT video about it. Of course, as always happens in my channel, very unpopular video. But I wanted to put it in for the record. I want to come back to those videos. It's one of those that it's really for myself. If there's like 20 people out there who want to watch that sort of video, great. It's okay. So anyways, mod 6 has zero divisors. There's the four places where it happens. And it's at 3 times 2. So 2 and 3 are zero divisors. And then 4 times 3. So 4 is also a divisor. Then when you do something like mod 8, 4 is a zero divisor, 2 is also a zero divisor, and 6 is a zero divisor. 6 times 4 is 24. 24 mod 8 is 0. Then I also did 9. Look at how pretty that pattern is. Yeah, I had a lot of fun with that. Every ordered integral domain is infinite. Try to prove of that. Yeah, so some of these problems I think were okay. Of course, I wish I had examples, and I wish I had a way for somebody to grade me. Maybe someday I will do that, take another course. This year it just didn't work out. Skipped the number theory stuff, went down to section 3.7, and then section 3.9. More integral domains. Yep, just determine whether something is an integral domain or not. Of course, the key here is you try to take two different members, multiply them, and see if the product is still in that domain. And of course, if it's not, then you knock it out. That's it. It's a no. Or you add them, or you divide them. If you divide them, and the device, what you come out of, is not in that domain, then it's out. That's usually just a trick, or the way you do it. I should say it's not even a trick. Then I picked a couple where I actually went through. So I did it for Z5, the ring of integers modulo 5, and I did go through and prove all the axioms. Then there was some more examples that I worked on. Yep. And then an ordered field. And then this is the Cauchy-Schwarz problem where I knocked my head for a little bit and at some point gave up, but you know, at least I tried. I need to try hard problems, and I'm going to do more of that in the future. I'm planning to. So here I did subfields, and of course, and I think I'm correct in the ones that I did, which I did them all in problems 3 and 4. I think the key is a subfield also has to be a field. So for example, a plus b 2 to the 1/3 is not a subfield because it's not a field. When you multiply two of these, you're going to get 4 to the 1/3, which is clearly not a member. That doesn't work. And of course, at least from what I'm seeing, and I hope to be correct, whenever I read a plus b square root of 2, ab is an integer, I'm like, forget it. Because when I divide them, I'm going to get a rational. But if it says a and b are rational, so I'm like, oh, there's hope. Maybe it is a field. And so, yeah, there you have it.